Now, you may have noticed that multiplication of multi-digit numbers is time-consuming and error-prone. So we would like to have a method of checking our work when we've multiplied two multi-digit numbers. So let's suppose that we've just multiplied 8,624 times 257, and we've gotten 120,736. And we want to know whether that answer is reasonable. We multiplied a big number by a big number and we got another big number. Is it big enough? Too big? What? What's going on? How can we know? Here's how we can know. We can check by rounding each of our factors and multiplying the result. We'd like to round each of our factors to make the multiplication as easy as possible. We'd like to round them to one non-zero digit. Now notice, this is different than when we estimated a sum or a difference. With a sum or a difference, we rounded each number to the same place. And the reason for that is that with a sum or a difference, it matters how the place values line up. But when we estimate a product, we just round each number to one non-zero digit because it doesn't matter how they line up. And we want to avoid multiplying numbers with more than one non-zero digit if at all possible. All right, so how shall we round these numbers? Again, we're estimating 8,624 times 257, and we want to see if our answer, 120,736, is reasonable. So let's see. 8,624, we want to round it to this leftmost place. What do we get? This next digit is a 6, so that tells us to round which way? Correct, up. We'll round up to 9,000. 257, we want to round to this leftmost place again. So this is between 200 and 300. The 5 tells us to round up to 300. So now we're going to multiply 9,000 times 300. We'll look at 9 times 3. 9 times 3 is 27. And then that will be followed by 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5. 2,700,000. Is 120,736 reasonable? Heck no. Let's try that multiplication again, shall we? When we have a huge difference like this, my guess at our mistake would be we'd forgotten to shift each line over. Let's try that again. 7 times 4 is 28. 7 times 2 is 14, 15, 16. 7 times 6 is 42. Add in the 1, 43. 7 times 8 is 56. Add in the 4, 60. 5 times 4 is 20. And again, this is the digit in the tens place. We write the first digit of our answer in the tens place. 5 times 2 is 10, 11, 12. 5 times 6 is 30, 31. 5 times 8 is 40, 43. Then 2 times 4 is 8. 2 times 2 is 4. 2 times 6 is 12. 2 times 8 is 16, plus 1 is 17. This looks more like it. Adding up, I get an 8 in the ones place, 6 in the tens, 3 and 2 is 5, and 8 is 13. 1 and 1 is 2, and 4 is 6. 6 and 3 is 9, and 2 is 11. 1 and 4 is 5, and 7 is 12. 1 and 1 is 2. 2,216,368. That looks more like it's in the right ballpark. These numbers are still pretty far apart, right? If I rounded this number, I wouldn't necessarily get this one, but they're in the same general vicinity, right? The furthest to the left digit agrees, and most importantly, they have the same number of digits. So this answer agrees pretty well with this estimate. Our estimates are going to be off by a fair amount, but not by this much. I'm going to have you try one of these now. Estimate the product 62,539 times 7,894. Again, round then multiply. Don't spend your time doing this multiplication by hand. Okay, so we're going to round each number to have one non-zero digit. 62,539, we want to round to this leftmost place. This number is between 60,000 and 70,000. The 2 here tells us it's closer to which? Right, 60,000. 7,894. We want to round this also to have one non-zero digit. This number is between 7,000 and 8,000. The 8 here tells us that this is closer to 8,000. So this product is approximately 60,000 times 8,000. That's going to be 6 times 8. 6 times 8 is 48, followed by 1, 2, 3, 4, 5, 6, 7 zeros. 1, 2, 3, 4, 5, 6, 7. That's 480 million.